Good evening to all. Today I am going to discuss about thermodynamic process for constant pressure. In fact, in the coming videos we are going to cover all five processes, that is constant pressure, constant volume, constant temperature, isentropic, polytropic, under the head of ideal gas as well as real gas. So total 10 processes, 5 for each ideal and 5 for real gas application is going to be discussed. Today we are going to discuss only on the constant pressure process, that is also called isobaric process. And I'm sure that this video is going to be very interesting. So please do subscribe my channel, and also don't forget to you know hit the bell icon. So thank you. So let's begin the discussion about thermodynamic processes for ideal gas. So before that, let's understand the thermodynamic system. So when you call a thermodynamic system, let's say compressor compresses the transfers the energy to the gas. Similarly, high pressure of gas generates power through the turbine. So what is then called thermodynamic system? Is it compressor? Is it turbine? Or it is gas? Yes, it is the gas which is called the thermodynamic system, not the compressor, not the turbine. So when we call thermodynamic system, that means our focal point is the gas. Gas can be hydrocarbon gas, gas can be air, gas can be nitrogen. Any other gas is considered as a thermodynamic system. So in thermodynamic system, there is a sign convention that we should follow. If heat is transferred, that is heat is added to the system, it is considered positive. When heat is taken from the system, it is considered negative. When work done by the system, like high pressure energy generates power by through the turbine, it is considered positive. When work is done on the gas or on the system is called negative. That is like compressor generates a compressor gives or compresses the gas and transfers the energy to the gas or thermodynamic system, it is considered negative. Similarly, for the energy transfer, if the level of energy increases, it is considered positive. When the level of energy decreases, it is considered negative. In case of compressor, energy level increases, so it is considered positive. In case of turbine, where high pressure energies becomes low pressure energy because generation of the power by the turbine, and so it is considered negative energy level. Now, types of thermodynamic system, that is open system, closed system, and isolated system. Here you can see this is open. This is example of open system. There is a flow of the gas comes in and goes out, so there is a transfer of mass and energy both, it is considered open. Similarly, closed system, there is a no mass transfer, it is closed inside the piston cylinder arrangement, only energy can be transferred, so this is closed. In isolated system, neither mass transfer occurs nor the energy transfer, it is called isolated system. In thermodynamics, most of the cases in real life application comes under the open system, but sometimes in the closed system, but in rare case it comes as a isolated system. Now, ideal gas equation of states. So ideal gas for the ideal equation of states for the ideal gas, it is written as PV is equal to nRUT. PV is equal to, and for n we can write a small n upon capital M RUT, and so we can write P into V by M is equal to RU upon M into T, and in short we can write P a small v is equal to R into T, where P is the pressure in Pascal absolute, V is the volume meter cube, small v is a specific volume, that is meter cube per kg, T is the temperature degree Kelvin, M is a mass of gas kg, capital M is a mole weight of gas, that is kg per kilomole, RU is universal gas constant, that is 8314.5 joule per kil joule per kilomole per Kelvin. R is the gas constant, that is joule per kg per Kelvin, and N is the number of moles, that is constants. So this equation is going to be used everywhere. So let's focus on this. PV is equal to RT. R is the gas constant. Now work transfer. If you look at the work transfer in case of closed system, in case of open system, in case of closed system, it is written as W is equal to integration of P into dV. This is a standard equation. And so if you look at on PV diagram, that is P in the y-axis, V is the specific volume x-axis, you will see that area, and let's say 1 and 2 is the compression process, again 2 and 1 is a again expansion process. So in this process, you can see, if you see the area under the curve 1 and 2 on x-axis is called the work. Similarly, in open system, it is considered minus VdP. This is standard formulas. So in this case, if same curve, the area on the y-axis, that is on pressure, is called the work for the open system. So please remember that if area on x-axis on, that is a specific volume on under the curve, is called work done for the closed system, and area under the curve on y-axis, that is on pressure, is considered work done for the open system. As I said, work done by the system is positive and work done on the system is negative, and work transfer per unit mass is called work head or head. So it's joule per kg. Now what about the energy transfer? Energy transfer for the closed system is called internal energy change. It's same thing, but energy transfer for the closed system is written as integration of CVdT, that is internal energy change, same as closed system. Similarly, for the energy transfer, the open system is called the enthalpy change, and energy transfer for the open system is written as integration of CPdT. So again, these two formulas are very vital, so keep on remembering these formulas. And energy of system increases, it is considered positive, and energy of system, if it decreases, it is considered as a negative. Now, as per the first law of thermodynamics, heat transfer is equal to work transfer plus energy transfer. So we can write Q is equal to W plus E. Please note that this is very important information. The first law of thermodynamics assumes efficiency of the thermodynamic machines is 100%. Means there is no losses during the transfer for work, energy, and or heat. So in first law of thermodynamics states that whatever is your work transfer, energy transfer, or heat transfer, all are ideal, that is 100% efficient. There is no losses, no efficiency of that system is considered 100%. Now let's discuss on constant pressure, that process, that is isobaric process for ideal gas. If you look at on PV diagram, since pressure is constant, 1 and 2 process, P is constant, again 1 and 2 is constant. So 1 and 2 on top is heating process, again bottom 1 and 2 is a cooling process, but pressure is constant, so this is two lines. Similarly, this is also shown on the TS diagram, that is temperature entropy diagram. So 1 and 2 is increasing temperature, increasing entropy, 1 and 2 is decreasing temperature, decreasing entropy. So again the constant pressure curve, this is also constant pressure curve for PV diagram, this is constant pressure curve for the TS diagram. So in thermodynamic process, it is a constant pressure process. When heat is added to the system, volume and temperature both increases as pressure remains constant. This is as per law. Similarly, when heat is removed from the system, volume and temperature both decreases as pressure remains constant. Now we have to derive the work transfer equation. So if you look at this, this is a PV diagram. As you know, the integration or area under the curve on x-axis is called the work head or work transfer. On constant on closed systems, we are discussing on closed system. So how we can derive, this is a constant pressure process, so pressure remain constant, so P is equal to P1 is equal to P2, because in, let's say, one state, two state, all are same, that is P1 is equal to P2 is equal to P. For ideal gas equation, we know P small v is equal to RT. Just now we have seen this. So we can write P1 V1 is equal to RT1 and P2 V2 is equal to RT2. So we can write V2 by V1 is equal to T2 by T1. This is come from this because P1 and P2 same. Another relationship is for ideal gas, Cp minus Cv is equal to R. This is another relationship. So using these two relation, we can derive the work transfer equation. So W is equal to integration of P dV. So we can write P is constant, V2 minus V1. And so if you take out P1, we can write P V1 is equal to V2 by V1 minus 1. But P is equal to P1. So we can write P1 V1 is in bracket start V2 by V1 minus 1. But again, P1 V1 can be replaced as RT1 and V2 by V1 we can replace by T2 by T1. So we can write work transfer per unit mass W is equal to R bracket start T2 because T2 comes here, so T2 minus T1. For the total work transfer, just multiply the mass. So we can write MR T2 minus T1. So these are the expression for work transfer for the closed system. You can see the area under the curve on x-axis is work transfer. Now, second step, we have to find out the energy transfer per unit mass. We can write energy transfer is equal to, since it is a closed system, we can write CVDT. So energy transfer per unit mass, we can write E is equal to CV T2 minus T1 because T has changed, T2 minus CV is constant. So, but if you want to calculate the total energy transfer, we can write E is equal to mCV bracket start T2 minus T1. Now we need to find out the heat transfer per unit mass using the first law of thermodynamics. Q is equal to W plus E. So you have to R into T2 minus T1 plus CV into T2 minus T1. So we can write common T2 minus T1. We can R plus CV. So R plus CV is nothing but Cp. So we can write heat transfer per unit mass is equal Q is equal to Cp into T2 minus T1. For total heat transfer, you just multiply M mass, so M Cp into T2 minus T1. So again, area under the curve on x-axis on TS diagram, it will give you the heat transfer. Now the same, parameter we need to find out for entropy change. So entropy change per unit mass S is equal to Q by T, but heat transfer just now we see Q is Cp into T2 minus T1. So we can write integration of Cp dt. So S is equal to Cp upon T into dt, and Cp is out 1 by T into dt is a log, natural log, that is ln. We can write ln is a natural log base E. So Cp ln T2 by T1. So this is entropy change per unit mass Cp log T2 by T1 or ln. But total entropy change just multiply with mass. So m Cp ln T2 by T1. You can see on TS diagram. So when heat is temperature increases, entropy is also increases because as per this equation. And if temperature decreases, the temperature ratio we can say it is increases, and there is increase of entropy. If temperature ratio decreases, there is a decrease of entropy. This is as per equation. This. Now we need to find the heat transfer, work transfer, etc. for the open system. Again, this is what is called constant pressure process. We can write this process, but again the same equals PV is equal to RT, P1 V1 is equal to RT1, P2 V2 is RT2. So we can write V2 by V1 is T2 by T1. Again, ideal gas relation Cp minus Cv is R, but as per formulas, W is equal to minus V dP integration. But since pressure is constant, so there is no work. So W is 0. So even total mass is also 0. You can also see area on the y-axis is 0 because this is a straight line. So there is no area. That is why you can also see the work transfer is also 0 for constant pressure in open system. Now the energy transfer we know Cp dt for the open system. So we can write Cp T2 minus T1. So for total, we can write total mass M into Cp T2 minus T1. Now heat transfer as per the first law of thermodynamics, you have to add both. We can write Q is equal to Cp T2 minus T1. So in short, we can write Q is equal to Cp T2 minus T1. For the total mass, we can write multiply total heat transfer Q is equal to mCp T2 minus T1. Again, the area under the curve on x-axis on TS diagram, this will give the heat transfer. You can show here there is a heat transfer. Entropy change, we can write same, S is equal to Q upon T, Q is equal to Cp T2 minus To, so we can write Cp dt because we can write in integration form. So Cp integration of Cp upon T into dt, so we can write Cp log natural log, that is ln T2 by T1. This is the entropy change per unit mass. S is equal to Cp natural log, that is ln T2 by T1, and for total entropy change we can write m into Cp ln T2 by T1. You can see here the TS diagram. Entropy increases, entropy decreases based on the ratio of T2 by T1. Now let us understand with an example. Nitrogen, this is an example. Nitrogen gas has initial pressure and temperature are 0.5 bar gauge and 30 degrees Celsius. Heat is added to thermodynamic system such that the final temperature reaches to 90 degrees Celsius on constant pressure process with consideration of ideal gas. Calculate work, heat transfer, energy transfer and entropy change during this process for considering closed system as well as open system. So we need to find the both case for closed system, another for open system. Also calculate inlet and outlet specific volume. Following data are given: mole weight of nitrogen 28 kg per kilomole, universal gas constant 8314.5 joule per kilomole per Kelvin, specific heat capacity at constant volume 20.8 kilojoule per kilomole per Kelvin, and local barometric pressure is 1 bar absolute. So these are the equation. These are the question. This is the question. With following data, we need to find out uh, work transfer, heat transfer, energy transfer, entropy change for the closed system as well as the open system. So since I have made the solution based on the Excel file, so I have seen here. So first of all, local barometric pressure is given 1 bar. Absolute temperature we know 273.15 degrees Celsius. So when we need to convert the inlet pressure into absolute pressure, so you have to add this local barometric pressure. It is given 1. So you have to add 1 plus 0.5, it becomes 1.5. Similarly, inlet temperature 30 degrees Celsius. So it is written T1G. When it written absolute, that is T1, then you have to add it 30 plus 273.15. We need to add. Outlet temperature is 90 degrees Celsius. So when it is written T2, that means 90 degree plus 273.15, that is absolute. M is a mole weight. It is written 28 kilojoule per kilomole. A specific heat capacity at constant volume, that is CV, it is given 20.86 kilojoule per kilomole per Kelvin, and universal gas constant RU is given joule per kilomole per Kelvin, that is 8314.5. So these data are given. So whenever local barometric pressure is given, you have to add whatever number barometric pressure is given to the gauge pressure to make it absolute pressure. When no data is given, you have to add a standard value, that is 1.013 bar absolute. Now the further calculation, we need to calculate gas constant, that is R is equal to RU by M. Just dividing, it will give 297 joule per kg per Kelvin. Specific heat capacity at constant value CV. Now we are converting in joule. It was given kilojoule, so CV into 1000, that is for conversion of joule, divide by mole weight. It will give you now joule per kg per Kelvin, that is 745. A specific heat capacity is constant. Oh, this is again mistake. It should be pressure, not the volume. It is Cp, and Cp is equal to Cv plus R. So we can add R, we know, Cv is known. So if you add these two, it becomes this 1042. And also we can calculate K, Cp by Cv. Both are given. We just divide this divide by this. It will give 1.4. Now we can find inlet specific volume. V1 is equal to R at T1 upon P1, and but P1 is a bar, so multiply 10 to the power 5 for Pascal. So if you convert this, this comes as 0.6 meter cube per kg. Outlet specific volume V2 is V1 into T2 by T1, so it is coming 0.719. Work work transfer W is equal to R into T2 minus T1. It is coming 17,817 joule per kg. Energy transfer CV T2 minus T1, it is coming 44,700 joule per kg. And heat transfer, if you add these two, or you can use CP T2 minus T1, both well the same, it will coming 62,517. And entropy change, it is CP log natural log T2 by T1, it is coming as 188. So this is for the closed system. For the open system, the only change will be work transfer, energy transfer, and heat transfer. So work transfer is a 0 because process is constant. Energy transfer is CP T2 minus T1. It is 62,517. So Q will be W plus E, which is same 62,517. And entropy change CP into natural log T2 by T1. It is coming 188. So I hope you have enjoyed for understanding the process for constant pressure and how the work transfer, energy transfer, and heat transfer occurs, closed system as well as open system. So thank you for watching.